All right, down to the last chapter. Okay, but if I do happen to get through this stuff faster than expected, I don't think anybody's going to object.
Okay, that's one side of you.
Okay. And in fact, there are certain parts of these notes that are less important than others, so I won't. I'm not going to go through everything because I have 6 pages of notes.
For today?
Yes, which is too many. But yeah, some things I could see glossing over. Right. So this chapter we get into time independent problems.
Be ambitious.
PDE. Okay. All right. So a few quick words about the Laplacian. A lot of them are, for the last several chapters actually, you know what, I think all the chapters. We've only been doing PDE with, well, most of the time one spatial variable, x, and then a time variable. But here we have 2 spatial variables and no time variable. So we hadn't really had much need for a Laplacian here, except for like in chapter 3 that came up. We just had like UXX. But the Laplacian in general, written many ways, delta U, also known as gradient squared U. And that notation comes about because it's literally the divergence of the gradient. Okay, so these 2 symbols actually mean different things. This is the gradient, this with a dot is a divergence operator. And that would be equal to uxx plus uyy plus uzz, or just uxx plus uyy if we're in 2 dimensions. So this comes up in all the important PDEs, heat equation, wave equation, but we're going to focus on elliptic PDE that involve the Laplacian. So we have Laplace's equation. Laplacian is equal to 0. And that would include boundary conditions, and I'll talk a lot more about the boundary conditions a little bit later on. And then we have, this is a special case of Poisson's equation, where Laplacian u is equal to some given function f of f of xy or xyz. And again with boundary conditions. So instead of solving initial boundary value problems like we have been, we're going to be focusing on boundary value problems, or BVP. Okay. Now, so one interesting aspect of the Laplacian, especially in 2D, plus uxx plus uyy. And for the most part, we'll be focusing on 2-dimensional problems. And at some point later in the chapter, we'll get to separation of variables in 2 dimensions. So there's an interesting interpretation of Laplacian, but this only applies in, let's see, yeah. Okay, well, since Laplacian in this case is, as I'm looking at formulas here, I think, should this also apply in more than 2 dimensions? Okay. Oh, yes. Sorry. Yeah, this the result I'm about to give you does apply in higher dimensions as well. So in 1D, it's just uxx, it's just the second derivative with respect to x. So you've been working with PDE involving Laplacian for several chapters, whether it's really been acknowledged that way or not. So here's the, in 1D, because it's so simple to work with, we can actually, I just spotted a typo in the notes. It's a lot easier to work with just because of the just because it's only the second derivative. Now, okay. So the 1D case, this is worked out in the notes, that if I look at the integral over an interval centered at x naught and with a radius of h, so I'm integrating from x naught minus h to x naught plus h of u of x dx, and I'm dividing by 2h, so this is the average of u on this interval, x naught minus h to x naught plus h. Okay. So if you expand u in a Taylor series around x naught, and you carry out the integration, so I'll refer you to the notes for details, what you get is u of x naught plus h cubed. Let's see, actually, I need to divide this by 2h. So h squared over 6 u double prime at x naught plus other terms that are higher powers of h and therefore relatively negligible. But this is the Laplacian of u at x naught.
Remember the first derivative term.
What happens is, because we're
You divide
integrating
by
on a
2.
symmetric interval,
All those cancel out.
yeah, it just goes to 0.
Okay.
Yeah.
Okay.
Okay, but details in the notes. Okay. So what does this mean? This means that if the Laplacian is positive, then that means that the average of u on this interval is going to be greater than the value of u at the center. So it means that u is less than the average of its neighboring values. Okay. Similarly, if Laplacian is negative, so then u of x naught is greater than the average of neighboring values. And then finally, if Laplacian equals 0, the u of x naught is equal to the average of neighboring values. So I didn't feel like writing out all of that 3 times. And in fact, this particular property, which is called the mean value principle, and I'll state that more formally later on in higher dimensions, is very useful to us in proving things about solutions of Laplace's equation or Poisson's equation. So this is an interesting interpretation of Laplacian to keep in mind. I've only shown it here for the one-dimensional case, but it also applies in higher dimensions. Okay. And in fact, yeah, so I'll prove a version of this in higher dimensions for 2 dimensions. About the Laplacian being equal to 0 and u is equaling the average of its neighboring values. Okay. So, so we're going to get into basic properties of elliptic PDEs. Now, if, first some terminology, if u is a solution of Laplace's equation, so its Laplacian is equal to 0, then we say that u is harmonic. So any harmonic function is a solution of Laplace's equation. I'll be using that term pretty frequently. Okay. Now, one way in which we can interpret Laplace's equation is, you think of it as a steady state of a time-dependent PDE. In particular, the heat equation, which is du dt is equal to Laplacian. Well, if a solution u converges to a steady state, so in other words, u is no longer changing over time, that just means you set du dt equal to 0, so the heat equation becomes Laplace's equation. Now, a similar thing would be true if we have some sort of source term, like a heat source. I'd have some term f of xt in here. We have a steady state, then Laplacian of u is equal to minus f is the describes the steady state temperature distribution. So Laplace's equation is very important in that case, that a certain time-dependent PDE have a steady state solution. You can analyze that steady state solution in terms of Laplace's equation or Poisson's equation. Now I mentioned the heat equation here. There's also a wave equation, which is utt equals Laplacian of u. But solutions of the wave equation often don't have steady state solutions. Because waves just tend to keep propagating, they might damp out eventually. So it's conceivable to have a steady state solution for wave equations in general, but this simple form of wave equation, utt equals Laplacian u, that in general, there is no steady state solution. That's because of how waves propagate, they just keep on going.
Generally, no steady state. Like in which cases might it have when utt equals 0?
Well, so because for instance, actually, as I say generally because I wanted to allow for possibility certain initial data might lead. Then again, like if your initial data f of x, like u of x0, for non-zero initial data, you're always going to have f of x propagating. Like if you think in terms of D'Alembert's solution.
Right.
So in fact, yeah, for a simple form of wave equation, yeah, it really is impossible to have a steady state. I'm always more careful about like off-the-cuff statements in case I might be wrong. But yeah, so I was hedging my bets there. But certain upper wave equations, if you have extra terms, like that might have some damping. Like for instance, in the first ODE class, I know when I taught it, we studied spring mass systems. And first a case where there's no damping, so mass would oscillate on a spring forever. But then you include a first derivative term to have damping, and the solution would eventually disappear over time. So if you have extra terms here besides Laplacian, you can get a steady state. But just not this one. Okay. So that's a nice physical interpretation of Laplace's equation. Okay. Here are some boundary conditions. So we need boundary conditions to ensure a unique solution. So first case, we have what's called the Dirichlet problem. That's where Laplacian is equal to f, where f could be 0. So this accounts for both Laplace's equation or Poisson's equation. And I'll state these in a 2D case, but they're higher dimensional variations. So some domain D is your PDE that's satisfied, and then U is equal to some given function G. Oh, I'll write it on full. So U of xy is some given function G of xy for xy on the boundary of D. So this is a notation that's used now, and I haven't used it lately. So a partial symbol expressed like this refers to the boundary of a domain. Okay. So this is the same kind of Dirichlet conditions that you're used to. You're specifying a value of a solution on the boundary. And then you can imagine what the other variations would be. The Neumann problem. So Poisson's equation on D, and then we have the normal derivative of U, which is, so that's the gradient of U dot product with a normal vector n. So this is the unit outward normal vector. Is equal to some function G. Okay. So to draw what's happening, here's your domain, a generic blob. So here we have, should be orthogonal, normal to the boundary. Okay. Now, this is consistent with the Neumann boundary conditions you've been dealing with Sturm-Liouville problems, because what is your Neumann boundary condition in that case? It's du dx is equal to something. Well, in the one-dimensional case, you're on some interval AB. What's the outward normal? Is this direction or this direction? Well, these are -1 and 1. So they're still vectors. They're just in one dimension. So what we have is, in this case, gradient of U dot product with your normal vector is just du dx dot product with plus or minus 1. So it's just plus or minus du dx. So Neumann boundary condition, you're specifying a value of minus du dx at the left boundary and then du dx on the right boundary. But we just always write them as du dx just for simplicity. But it's the same thing. You're still taking a directional derivative. It's just that in one dimension, you only have these two directions, left or right. And then finally, we have the Robin problem. That's mixed boundary conditions. So same PDE, Laplacian is equal to f, and then you have some linear combination of boundary conditions. So we have u plus alpha du dn is equal to some given function g. Okay, on the boundary. So, so those are the three general kinds of boundary conditions that we deal with. And mostly we deal with the first two, but the Robin problem is definitely of importance in applications also. Okay. Now what's kind of weird is you can have Dirichlet, Neumann, or Robin boundary conditions with all kinds of PDE, including time-dependent ones. That's what we've been seeing in recent chapters. But for some reason, the term the Dirichlet problem just refers to this, of Laplace's equation or Poisson's equation. Okay. Now, so one interesting thing about these different problems is the question of existence and uniqueness. That generally speaking, you're going to have a unique solution of a Dirichlet problem. However, you might not have even existence of a solution to the Neumann problem. And something to keep in mind is you're definitely not going to have uniqueness. Because if I take any solution of a Neumann problem, so it solves a PDE and satisfies the boundary condition, I can add any constant to the solution and it's still a solution. Why is that? How come adding a constant doesn't matter?
Because they're the same gradient.
Yeah. So the gradient's not going to change, and
Yeah.
these are second derivatives, so they're not going to change either. So yeah, because all of the conditions on U involve derivatives of U, you can always add a constant and still have a solution. Okay, so that's like, so I'm going to summarize this questions of existence and uniqueness. Almost forgot to move this. All right. Okay. So for Dirichlet and also Robin problems that you have existence of a solution and uniqueness. If a boundary of D is sufficiently smooth. Sometimes corners in the boundary can present a problem. Okay. All right, but things are generally well behaved there. For a Neumann problem, you do not have uniqueness because you can add a constant to the solution. And you only have existence, and I say only if, because what I'm stating is a necessary condition, that the integral over the boundary of D, of your boundary condition G, must be equal to the integral over the interior of your domain of your right-hand side of your Poisson's equation F, which would be 0 if it's Laplace's equation. And it turns out it's pretty easy to prove that this condition must be satisfied. I should say that this is referred to as a compatibility condition. Because what it's saying is, because generally your boundary data, G, and your right-hand side, F, those are independent functions. They generally have nothing to do with one another. But it turns out now there is a dependence between them. So for given F, you just can't choose any old G and expect to have a solution. So that's why, in other words, the various pieces of data for your Neumann problem have to be compatible with one another. Okay, so to prove this, all we have to do is take the integral over your domain D of big F, but U satisfies PDE, so this is equal to the Laplacian. But what is the Laplacian? That is the divergence of the gradient. And what we do at this point is use the divergence theorem, which says that the integral over the interior of the divergence of something is equal to the normal component of that something over the boundary. But what is this? Gradient, the normal component of gradient, that is the normal derivative. Yes, you're getting one step ahead of me. But yeah, this is normal derivative, which is specified by the boundary conditions to be equal to the integral of g. Okay. So, so because of the divergence theorem, which is very important working with Laplace equation in general, and something good to keep in mind, we get this compatibility condition. Okay. All right. Now, in some cases later on in the chapter, we'll be solving Laplace's equation or Poisson's equation on like a rectangle. We would do the same old separation of variables. So it works out fairly similar to what you've seen. But we're also interested in solving these equations on other geometries, like on a circle, so you need polar coordinates, or a cylinder, so you need cylindrical coordinates, or a sphere, so you need spherical coordinates. So we have to be able to express the Laplacian in these other coordinate systems. So I have in the notes a long-winded derivation of the Laplacian in polar coordinates. I'm just going to spit out the result here. So you end up with a very different sort of PDE to solve in these other coordinate systems, and you also, so then you get very different ODEs to solve when you perform separation of variables. So you can still do separation of variables, but okay then.
Sorry.
All right, so polar coordinates, you have x is r cosine theta, y equals r sine theta, and go the other way, we have r is square root of x squared plus y squared, and tangent of theta is y over x. I'll give you a quick rundown of how you would perform a conversion. Because what you do is, if you you can change your derivatives in your original variables to derivatives with respect to your polar variables. So du dx is u r rx plus u theta theta x. And similarly for uy, so I won't repeat that. And then you can do this again for uxx. So that would be, so if I go to take the derivative of all this with respect to x, well that is u rx rx plus u r rxx plus u theta x plus u theta theta xx. That was creepy.
Super creepy.
But then I could go a little further because u rx is the same as u x r. And now I can take this and differentiate it with respect to r. Okay. So this formula right here. So I'm going to have URR Rx plus U R theta x. So differentiation with respect to okay. Actually, that's probably not the best way to do it. Okay. In fact, no, I'm not going to do it that way. Okay, so if I go back here, wherever I see U, I plug in UR. So that's why I get URR Rx plus UR theta x. Okay. So now I can work that in down here. So I get URR Rx, so that's Rx squared, plus, and then I would handle this U theta x in a similar way. So I'm going to get 2UR theta Rx theta x plus U theta x squared. And then you have first derivative terms, UR Rxx plus U theta xx. And then Uyy is similar. So now we have these nasty expressions for your original derivatives. But the thing is, I needed these expressions like Rx, Rxx. How do you compute those? You differentiate these implicitly. So for instance, I want Rx. So dr dx is equal to the derivative of this with respect to x, which is just going to be x over the square root of x squared plus y squared. But I want to express that in polar coordinates. Well, that's r cosine theta over r. That's just cosine theta. Now, what about Rxx? So I need to differentiate this with respect to x again. So Rxx is going to be derivative of cosine theta with respect to x. That's going to be minus sine theta times the derivative of theta with respect to x. Now, what is d theta dx? Well, tangent theta is y over x. So if I want to differentiate with respect to x, I get secant squared theta x is equal to the derivative of this with respect to x, which is minus y over x squared. So that tells me that theta x is equal to, I move this to the other side, cosine squared theta minus y over x squared. Now, if I plug in polar coordinates for everything, I get cosine squared theta minus r sine theta over r squared cosine squared theta. Well, the cosine squareds cancel out, and one of the r's cancels out, and I get minus sine theta over r. So now I can plug that back in here. So I get minus sine theta times minus sine theta over r, and I get sine squared theta over r. So that is Rxx. So I can do this with all the first and second partials of r and theta that I need. It's a very tedious process, which is why I'm not going to do the whole thing here. But I want to do these so you can get a general idea of how to properly carry out this implicit differentiation of r and theta. Actually, explicit differentiation is enough for this, but you need implicit differentiation here. Because you have not theta equals something, but a function of theta equals something. So any questions about how these crazy differentiations were carried out? So what happens is, after you write out uxx and uyy in terms of polar coordinates, which is an expression with 1, 2, 3, 4, 5 terms each of these, and then you combine them, and you have a lot of simplification. Some things canceling, and you have a lot of cosine squared plus sine squared equals 1 going on, and ultimately the Laplacian turns out to be urr plus 1 over r ur plus 1 over r squared u theta theta. So a bit more complicated than just uxx plus uyy. But this is if you do separation of variables, you get an equation for r and an equation for theta, and those are very well studied. Well, actually for theta, you still get the same old ODE that you're accustomed to, where you have solutions of sine and cosine and so forth. But the r equation is a bit more involved. And actually, let's take a look at the radially symmetric case. So u of r theta simplifies to a function depending on only r. Radial problems are very important, for instance, in reservoir simulation, oil reservoirs, where you're solving a PDE centered at like a well, an oil well. So that's like your origin. And the solution behaves in a radially symmetric fashion. In other words, it doesn't depend on theta. So those PDEs come up very often in that context. Okay, so then you just have Laplacian of u, which is urr plus 1 over r ur equals 0. I drop the theta term because u doesn't depend on theta. So the derivatives with respect to theta are 0. So what are solutions? Well, there's one obvious one. U is a constant. Because you're taking derivative of a constant, you only have derivatives over there, and you're going to get 0. The other solution, though, is more interesting. Minus 1 over 2 pi natural log of r is a solution. And this is called a fundamental solution. So this is definitely a more physically interesting one. Because notice, at r equals 0, this is undefined. It's going to infinity. Now, the constant, minus 1 over 2 pi, is not really needed. You can take any constant multiple of a solution, but it's more convenient if you have it there, basically. So, depending on what I cover in this chapter, we may come back to it. Okay, but I'll give a physical meaning of this. This is electrostatic potential due to a charge at the origin.
So it's at the origin itself there is no.
Or there's infinite, basically.
Okay.
Yeah.
Okay, negative infinity, so that there's a negative sign, so it's infinite.
Right.
Oh.
Yeah. Okay. Yeah. So Laplace equation is very useful for modeling electrostatic potential. Okay. All right. So that is polar coordinates, and we also have two other coordinate systems of interest: cylindrical and spherical. I won't go over derivation. I'll just write down what the Laplacian is. Well, for cylindrical, we already know it, basically, because cylindrical is just polar coordinates, and then you add z. But let's go ahead and write that down for completeness sake. Okay. Okay, so then we have, I like to refer to that as polar plus z. Once you have polar, then this is not very interesting. Okay, so we have Laplacian is u r r. So say Laplacian is in polar coordinates. And then you just tack on uzz. And then you have spherical coordinates. So spherical coordinates, you have x is equal to rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. So in those coordinates, so this is really nasty to convert. You have u rho rho. I feel like Astro from Jetsons. Rho rho.
That's Scooby Doo.
No, but it's Astro.
Is Astro?
Scooby-Doo is...
I think it's do both.
Or maybe.
There's some.
Yeah, Scooby does.
Scooby Doo also goes. "Ruh-roh."
Yeah.
No.
Yeah. Yes, he does.
Okay, fine. Well, I want proof though.
For real? Because I will Google it now.
Okay.
Already on it.
Okay, or Haley will Google it.
Okay. 2 over r u rho plus 1 over r squared u phi phi. And then a strange term here, cotangent of theta over r squared u phi. And finally 1 over rho squared sine squared phi u theta theta. Okay, so very complicated Laplacian in that case. But again, you want to do separation of variables to try to solve ODEs for r, or for rho, phi, and theta separately. Okay. Another thing I want to point out is Laplacian has certain symmetries. So if you have a harmonic function, so it's a solution of Laplace's equation, then certain variations of u are also guaranteed to be harmonic. So for instance, I can shift the coordinates in any manner, even if it's different shifts for x and y. And if I express in each polar coordinates, if I shift in theta, so here we're shifting. Here, since we're shifting the theta coordinate, that is a rotation. So any rotation of a harmonic function is also harmonic in 2 dimensions. And finally, dilation. Here for it in 2 dimensions, but it also works in 3 dimensions. So any dilation of a harmonic function is also a harmonic function. What's interesting is you can shift by different amounts in x and y, but here the dilation has to be the same. Otherwise, the derivatives won't cancel out in the Laplacian. Okay. Oh wow, really? Wow, I'm almost through the notes already. I'm kind of surprised. Okay. All right. I guess we're supposed to wrap up in 20 minutes or something, so you can get to analysis, or several of them anyway. All right.
3 more classes left. It's almost over. But it's almost over. And you signed up for his other analysis
I
class.
thought today real analysis was off.
No,
What is next move?
Thanks.
we're done after Wednesday.
We're done after one.
We don't have any wrong.
The final deal on
Yeah, we never have.
So if we can do the final, we don't have to show up.
So a very important and interesting property of solutions of Laplace's equation.
Anyhow.
And for those of you who choose homework to do homework 7, this is of importance for you. The maximum principle. Okay. So first I'm going to state the what's called the weak maximum principle. So basically says that now first notation. I have a domain D, but D bar is called the closure of D. And all that is D itself union with its boundary. Whoops, not sure why that omega is there. Boundary of D. Okay, so for example, the closure of the interval AB, the open interval AB, is just a closed interval AB, because you're including the boundary points x equals A and x equals B. Okay. All right. So the weak maximum principle says that the maximum, and by extension, the minimum of a harmonic function U, so solution of Laplace's equation, occurs on the boundary. Okay. So whatever extremes your function has, they must be assumed on the boundary. Okay. Now, a quick proof. I'm going to let v be equal to u plus this function type on epsilon x squared plus y squared. What this means is Laplacian of v is equal to Laplacian of u plus, if I take the derivative of this with respect to x twice and y twice, all I'm going to get is 4 epsilon, 2 epsilon from here and 2 epsilon from here. Okay, and Laplacian of u is 0, and I'm assuming that epsilon is positive. Therefore, Laplacian of v is positive. Now, what that means is v cannot have a local maximum in the interior of a domain. Because in order to have a local maximum, you need to have a gradient of 0, and your Hessian matrix has to be negative definite. And in order for that to happen, you actually have to have requires your second partial derivatives with respect to x and y be negative. Because what happens at a maximum in terms of concavity? Concave up or concave down? Maximum. You're drawing a minimum there. Okay.
It's concave up, right?
No.
If it has a maximum, it's got to look like that.
Yeah.
Mountain.
Concave down.
Concave down, right?
Yeah, which means these partial derivatives have to be
Looks like a mountain.
negative. Yes.
I always get that confused too. But I
Okay.
want to say maximum.
That's how I describe it on 101 students. It's either Denver or New Orleans. Negative.
Oh, okay, that works.
Well, they understand it, man.
It's really funny.
Well, because
Yeah.
I heard one student say that one time. They're like, so it's like a bowl like New Orleans. I'm like, yes.
Oh,
then it's Denver. Because New Orleans has a bottom, like a minimum. Like,
Yeah.
it's a bowl, and Denver has got a mountain.
Um,
Stop. Complete
since this can't have a local maximum, that means that
They know that, they don't imagine to get that.
so maximum v has to be assumed on the boundary. So it's a maximum within that closure. It's kind of like, for instance, in calculus 1, you're finding a max of a function on a closed interval. What do? You check for critical numbers and you check the endpoints. It's the same idea. We've ruled out the interior, any critical numbers that would lead to a maximum anyway. So then we just look at.
But then we are saying that it has a maximum, right?
Well, there is a maximum, but it must be on the boundary.
Right, but how can we sort of say that it has to have a maximum, right? Is there
Oh, because a continuous function on a compact set has a maximum.
okay.
And that's why we work with a closure of a domain, because then it's a closed and bounded set. So it's compact, so it's a maximum. Yeah. So then, just let epsilon go to 0. And then, so the statement that applies to V now applies to U. Okay. Now, if you keep in mind that this is about the maximum occurring on the boundary, but the maximum of the minimum of a function u, you could argue is if you take the maximum of minus u and negate it, and keep in mind that if u is harmonic, then minus u is also harmonic. Then this same logic can be used to state that the minimum must also occur on the boundary. Okay. Now, I should keep in mind, one thing to keep in mind though is this says the maximum and minimum must occur on the boundary. However, based on this, you could have a tie in the interior. This result does not explicitly rule that out. I mean, you kind of intuitively see that you could not have a tie based on how I've proven this, but I want to be able to prove convincingly that the max and min occur only on the boundary. That it's not possible to even hit the same value in the interior. But there's a little more to go through to prove that result. So I'm going to state another interesting result on the way to that. Well, in fact, here's what you could have. Suppose you have a maximum occurring on the boundary, and then as you venture into the domain, what if u is not changing at all? So if u is locally constant. So we could have this situation where it's not really a local max, so it's not up and going down and coming back up again. I'm not talking about that case. That has been ruled out by this proof here. But you could have something where it's at its maximum to boundary and then remains constant as you on certain directions go into the interior. So that's why you could have a tie. But I will prove a stronger result that almost always rules out a tie as well. Okay. All right, but first I need this result, which is very interesting in its own right. The mean value principle. And this says that if u is harmonic, on domain D, and if I choose a point x naught, y naught in the interior D, then that tells me that u is actually equal to this integral And this is equal to the average of u on the circle that has a center at x naught, y naught, and a radius, big R, provided that this entire circle actually lies within D. So R has to be chosen sufficiently small so that the disk is entirely contained in the domain. So in other words, U is equal to the average, its own average, on any circle centered at itself, which is quite a striking result considering how much U could supposedly vary. But if you look at any circle surrounding that point, so we have, that's not a very well drawn circle. So as long as these circles are contained within your domain, so your boundary is out here somewhere, I can average U on any of these circles and get the same value at the center. So that's one property unique to harmonic functions. Okay. So to prove this, okay, and actually there's not much involved here either. The maximum defined function v of r is this average now, I won't go through all the details here, but just give you the main idea of the proof. So this is equal to that. It's just written more compactly. It's the average of u on the circle, because this is the circumference of that circle. So it's integrating u over that circumference and then dividing by the length of that curve, 2 pi r. So you can show it. I won't go through the whole differentiation here, but you can write it out kind of like that. And what you get is, that this function actually does not depend on r at all. And the reason why, because the integral over the circle of the normal derivative of u has to be 0. That is a compatibility condition that I mentioned earlier. So that is something that still applies. So since the Laplacian is 0 throughout the domain, because this integral is equal to the integral over this d sub r. So d is the interior of Laplacian. But that integrand is 0. All right. So what would happen is, if you take a derivative of v with respect to r, you're differentiating its integral, you get the normal derivative. So this integral pops up, and now you can say it's 0. So what that means is, the average over the circle radius r does not depend on r at all. So it's not changing. But then what happens is, you let r go to 0. That tells you that this integral well, since it's the average over the circle, and the circle is collapsing to the point x naught, y naught, this average has to converge to the value at the center. And that's it. And the textbook has more details about how you would actually carry out this differentiation. But if you write out the integral like in this form, then you can, what you actually get, actually I can write it out. Derivative of this with respect to capital R equals du dx times the derivative of this with respect to R, which is minus sine theta, plus du dy times, hold on a second. Sorry, with respect to R. So this is going to be cosine theta. This is going to be sine theta. And the thing is, this is equal to the gradient of u dot product of cosine theta, sine theta. But if you look at a circle, the vector cosine theta, sine theta is this vector right here. That's your normal vector. So this is derivative, the normal derivative of u. So I just want just so you can see how this pops up. So you differentiate this integral with respect to r, and all you get is this normal derivative. But because this integral has to be 0 by compatibility condition, that's why the derivative of v with respect to r has to be 0. Again, it's not every detail, but a little more to go on with what we have. Okay. A little more time. Okay. So I've just proven that the if a function is harmonic, then it satisfies this mean value principle. But now, suppose we have a function that satisfies the mean value principle. Is it harmonic? And the answer is yes. So the view satisfies the mean value principle in a domain D. The view is harmonic. In D. Okay. Because, all right. Because by satisfying the mean value principle in D, what we have the following is 0 is equal to big R times the derivative with respect to big R of that integral. So 1 over 2 pi integral from 0 to 2 pi u of x naught plus big R cosine theta y naught plus big R sine theta d theta. Because all of this is equal to u of x naught y naught by satisfying the mean value principle. That is a constant. Therefore, of course, this derivative is going to be 0. So factor r is thrown in because it'll be convenient later. So now, if I carry out the differentiation, all right, I'm going to pull out this 2 pi. I'm going to differentiate this inside, and what I get is integral. Actually, this is what I was writing out a little while ago. Du dx cosine theta plus du dy sine theta d theta. And as I wrote out earlier, actually I should have just waited until now, this is gradient of u dot normal vector. But the thing is, when you take the normal component over vector field and integrate it over the boundary, then that's the same as the integral, okay, actually, okay. Oh, right. This becomes a 1 because this r gets absorbed inside here, because when we treat this is a line integral, and when you parameterize it, we have x is equal to r cosine theta, y is r sine theta, and that means that dx is minus r sine theta, dy is r cosine theta. So that causes a factor of r to actually appear in the line integral. And that's why once I condense this into a line integral over a circle, the r it goes away because it's actually part of the dx and dy. So, but here we use the divergence theorem. That the integral of a normal component over a boundary is equal to the integral of a divergence over the interior. But the divergence of a gradient is the Laplacian. And this is already known to be 0, but this is an arbitrary disk. The only way that this integral can always be 0, no matter what disk we use, is for the integrand, Laplacian, to be 0. Therefore, it is harmonic. Okay. Now, I know I'm at risk of cutting into Dr. King's time, but someone tells me that as many stories as he tells her in class.
This may be a little bit better.
What?
This may be a little bit more important.
Yes. Okay. So, but I really am, I'm down to like the last few lines. So now we have a strong maximum principle. Which says that if U is harmonic, shoot.
Check that on there. I just turned it.
What?
I just turned it.
Oh, okay. So it was pointing right before. Okay, thank you. All right, so if U is harmonic in the domain D, and if it assumes it's max or min on the closure of D at an interior point. So in other words, if we have a tie, we already know its max and min must occur on the boundary. But if there's a tie, also assuming it's max or min at an interior point of D, then U is constant. So that's the only way that can happen. And to quickly prove that, if U does assume it's max, we'll stick with max, at an interior point, then well, U is, because it's harmonic, is equal to its average on any disk. Okay, point, I'll call x naught, y naught like I have been. So U is equal to its average on any, sorry, not disk, circle centered at x naught, y naught that is contained within D. But the thing is, its max. Okay. But the thing is, its average cannot be greater than all its values. So the thing is, you're saying that you're expecting it to be greater than its surrounding values. But if it's greater than all of them, it cannot be equal to its average. So the average has to be somewhere between the max and the min. So the only way for this to happen is it has to be constant on each such circle. And because x naught, y naught is an arbitrary point, and because these circles are arbitrary, u has to be constant on the entire domain D. So it's this essential property right here. So you can function a certain variation, maxes and mins and so forth. These maxes, well, the absolute max or the absolute minimum can't be the average. So just a simple principle. The average of a set of values must be somewhere between the max and the min, obviously. So because u is equal to its own average, it can't be greater than those values. Okay. All right, that's it. Well, got through all the 6 pages of notes. So at least I'm on schedule. But now it means I have to write a full set of notes for Wednesday, which I'm not looking forward to. But okay.
If u has a max or min, its interior, it's a constant. Any other function will have its maximum at the boundary.
Yes, and only the boundary. That's
And
the
only
key.
the boundary.
Yeah.